Hi, chemistry. Today we're going to talk a little bit more about ionic compounds. Specifically, I want to look at the different parts of an ionic compound and walk you through understanding each of these parts. So, we're going to talk first about subscripts. So, subscripts are exactly what they sound like. Sub means below, and a script is something written. So a subscript are these little numbers that you see that are written below the actual typed font, and they're always numbers. So a couple things about these subscripts. First of all, the subscripts are describing a quantity that's present. In the beginning of the year, we talked about the difference between compounds and mixtures. And remember, if you had a compound like water, for example, there was no space inside that. So if you look at all these individual things we have written, there's no spaces anywhere in these molecules. One thing is written exactly behind the next thing. That's what makes these all compounds, right? If they were a mixture, you'd see a comma or that ampersand and symbol, right? There would be something with spaces indicating that you have two separate elements. So when you don't see any spaces, you have one compound. That means that all the atoms in this compound are bonded together somehow, and that one new compound has very unique properties. If you pull them apart into separate things, the properties are going to change, right? So these subscripts are indicating the number of things we have in our compound that's all bonded together. So for example, let's look at magnesium chloride over here. It's an ionic compound, and in this ionic compound, we have magnesium bonded to chlorine, right? This is indicating that we have two magnesium for every one, or two chlorines for every one magnesium. That's why that subscript 2 is right behind chlorine. It's indicating the two different chlorines. So how many of each molecule would we have here for the strontium and the nitrogen? Well, we'd have 3 strontium and 2 nitrogen. So if I don't know what it would look like if we wrote it as separate molecules, we'd have 3 strontiums and we'd have 2 nitrogens. Now, the way I'm writing these compounds, or the way I'm drawing these compounds, is a little misleading. I'm writing these compounds as if they exist as an individual little unit. But remember, anything that's an ionic compound, anything that's a metal and a nonmetal put together, which makes it ionic, they're actually not going to exist like this in individual little packets. Remember, they're really going to exist in a big lattice that has lots of these things present. So what those subscripts are indicating for ionic compounds is the ratio. For every 1 magnesium in your lattice, you're going to have 2 chlorines. It's indicating a ratio in your lattice. Now, for something like water is not an ionic compound. Water has a covalent bond. It makes it a molecular compound, right? So in this case, we look at the subscripts and we notice there's 1 oxygen and there's 2 hydrogen. And this individual little unit that we would like to call a molecule, that actually does exist. Water, when it's a liquid or a gas, it does consist of 3 atoms floating around together all by themselves, not hooked up to an individual lattice. Now in water, you can see another thing. Notice that it's H2O and there's nothing behind that oxygen. This leads me to my second point. That when there's a subscript missing, we always understand it to be 1. So we could write this as H2O1, indicating that there's 2 hydrogens and 1 oxygen. And this is true for everything. Look at NO. There's no subscripts in this one, right? Well, each of the missing subscripts can be understood to be a 1. So in that molecule, we'd have a nitrogen attached to an oxygen. 1 nitrogen, 1 oxygen in this molecule. As you look across this board, you'll notice that all kinds of different species have subscripts in their formula describing what's present. I mean, look at all the different types of species we have. We have ionic compounds here. We have an ion, a polyatomic ion there. These are all covalent compounds. Here's a covalent compound that's looking a little bit more complicated. Here's a complicated ionic compound. This one's also ionic. That one's also ionic. So we have a bunch of different things. We have ionic compounds that use subscripts, ions use subscripts, covalent bonded molecules use subscripts. You're going to see these subscripts across the board, and they always mean the same thing. Now, we talked about how subscripts describe the number of atoms or the number of ions that are present. Well, notice sometimes the subscript follows a parentheses, as in this 2, right? Notice how this 2 is behind a parenthesis. So what is it describing? If subscripts describe the thing that they directly follow, what is that 2 describing? Well, that 2 is describing everything in the parentheses. So basically, you're going to have a magnesium. You're going to have this bundle right here, and you're going to have that bundle twice. So it would look, if we drew it out, it would look something like this. We have 1 magnesium, and we have that bundle that contains nitrogen and 3 oxygens. We have that bundle of nitrogen and 3 oxygens twice. That's what the 2 behind the parentheses means. So notice what happens to this 3. This 3 is directly behind the oxygen. It means I have 3 oxygens for every 1 nitrogen. So if I have 3 oxygens per bundle, and I have 2 bundles, then how many oxygens do I have? I have 3 twice. So I have 6 oxygens in this compound. So that's what happens when you start to have parentheses. Now, you may recognize this bundle. Hopefully you do. If you don't recognize the bundle that's inside of these parentheses, go look at your ion sheet. Can you name what ion that is? NO3. It must have a charge if it's an ion. And you'll find that it's nitrate. That's the nitrate ion. So we have 1 magnesium, we have 2 nitrate ions. We have 1 magnesium, we have 2 total nitrogens, we have 6 total oxygens. So subscripts always describe the thing that they're directly behind, whether that's an atom or an ion or a parentheses that's containing something else. It can double or triple or quadruple a whole polyatomic ion, like in the case of nitrate. This also brings up a really good example. This magnesium and nitrate example bring up a good example that this is one of the reasons why you have to know your ions. We talked about ions before, and I got on my soapbox and I talked about how essential it is to speak the language of chemistry. You have to know the ions and their names well enough so that you don't always have to hold on to your ion sheet. And this becomes really apparent when we start looking at compounds. Look across this board that we have up here. Can you recognize polyatomic ions that are inside of these compounds? In order to name them, you have to do exactly that. So we talked about this one already, nitrate, and that one's kind of nice because they put it inside parentheses. So sometimes they put it inside parentheses and it's easier to recognize. Sometimes they don't. Like in this case, this is also an ion inside a compound. Can you name what ion that is? It's acetate. How about this compound? Can you see the polyatomic ion inside of here? It's ammonia. How about this compound? Can you see the polyatomic ion that's inside of this one? It's sulfate. So you have to know these ions well enough, be able to recognize the ions as a bundle so that you can separate a compound into the two things, one of them being one of your polyatomic ions. Another thing you'll notice on this chart is that all of these things are binary. And these are the only things I'm going to ask you to make, balance, and name are binary compounds. Bi means two. So they're going to have at most two ions present. And that's true for all of these that we just talked about. Sulfate is paired with the hydrogen ion. Nitrate is paired with magnesium. Acetate is paired with sodium. Ammonium is paired with chlorine. So notice inside these compounds, there's two things. So when you look at a compound and it looks crazy, take a deep breath and remember you only have to find two things inside that compound. One of them is going to be a polyatomic ion if there's more than two atoms present. Okay, one other thing I wanted to talk about with subscripts before we get going any farther on ionic compounds is that subscripts are found in elements as well. So the elemental form of an element is not always what you pull off the periodic table. So for example, if we're talking about elemental copper, if I want you to write elemental copper into a sentence, you would write it as Cu. And you would know that copper, because it's a metal, it's going to experience metallic bonding, and it's going to be a whole bunch of copper atoms bonded together into a metal lattice. That's elemental copper. We can picture what it is molecularly, and we can write what it is as a symbol, as a formula. Now, most things on the periodic table, most elements exist just like this, but not all of them. There are 7 elements that exist as diatomics. Diatomic molecules. And these 7 diatomic molecules don't exist as lattices, and we don't write their symbol as just the elemental symbol. So chlorine is an example of this. Elemental chlorine exists as a diatomic molecule. So if I ask you for elemental chlorine, what you have to write for me is Cl2, and what you imagine inside your head is a molecule with 2 chlorines bonded together. Now, these diatomic molecules exist as individual molecules, just like I've drawn it. They don't exist as lattices, which is why their formula is so important to get right. So these 7 diatomic molecules actually make a 7 on the periodic table. Let's see if I can remember them off the top of my head. If you start with nitrogen, then oxygen, fluorine, chlorine, bromine, and iodine. So elemental nitrogen exists as N2. Elemental iodine exists as I2. If I ask you to write elemental iodine into a reaction, you have to write it as I2, not I. So these 7 you have to remember. And actually, the 7 on the periodic table, you'll notice, is missing one. And the one that you're missing is hydrogen. Hydrogen is your 7th diatomic element. Now, there are other elements that form different forms. Sulfur is one of them, for example. If you have elemental sulfur, chances are you have an S4 molecule. Phosphorus forms a P8 molecule. There's a couple other ones on the periodic table that do something similar, but you don't actually have to know them. The only ones I'm going to require you to know for now are the 7 diatomic molecules because they're so common. They show up all the time. Sulfur and phosphorus are not quite as common. So you can write sulfur as S4 or you can write it as an S. You can write phosphorus as P8 or you can write it as P. Okay, so we're going to let those go for now and focus on the ones that show up over and over and over again, which are these 7 diatomic molecules. Their elemental form is actually as a diatomic molecule. So the subscript is really important. Okay, moving on. In ionic compounds, the subscript actually provides an additional service. So, yes, it tells us how many atoms are involved or how many ions are involved in the lattice or in the compound. But in ionic compounds, it actually shows us the ratio you need to come up with a balanced compound. So notice all of these on the board right now are ionic compounds, and all these ionic compounds are neutral. Notice none of them list a charge, right? So all of these compounds must mean that it's neutral. Now, a lot of people misunderstand this word neutral to mean that there's no charges present, and that's just not true. Remember, we're dealing with ionic compounds that are built out of ions. There's charges present. Neutral actually means the charges are balanced. So what this means is that the number of positive ions you have is going to be equal to the number of negative ions we have. Now we can see this in a very simple way for something like lithium fluoride. Remember, lithium forms an Li plus ion. Fluorine forms the F minus ion. If you have a 1 plus and a 1 minus, what's your overall charge? It's 0. The charges are balanced. So we include subscripts. In the case of lithium fluoride, it's 1 lithium to 1 fluoride, okay, to show that that's the ratio we need in order for these charges to be balanced and have a neutral compound or a neutral lattice. Now, some of them are more difficult to see. Let me show you a couple others, like magnesium chloride would be a good place to start. So, magnesium forms a 2 plus. Chlorine forms a 1 minus. If you add these together, a 2 plus and a 1 minus, you don't get 0, right? 2 minus 1 is not 0. And that's why we need the subscripts. The subscripts tell us we need 2 chlorines. So a 2 plus minus 1, that's going to equal 0. Strontium nitride is even more complicated. So strontium is a 2+ charge. Nitrogen is a 3- charge. How many of each of these do we need to be neutral? Well, we need 3 strontium and 2 nitrogen in order to be equal. So a 6+ and a 6- are going to be equal to 0. That's why you need the 3 subscript for strontium and the 2 subscript for nitrogen. And notice all of these, we just did the 3 on the top. If you go through and do the 3 on the bottom, you'll find the same thing is true. All of the charges are balanced so that there's the same amount of positive charge as negative charge, and you end up with a neutral compound. Now, it's one thing to observe this as being true like we just did. It's another thing to come up with it on your own. And so that is something that we will practice, coming up with these subscripts on our own in order to balance the compounds. Before we do that, though, I want to show you on a molecular level what this looks like. If we go back to something we just did, we can draw the Lewis dot structures for these atoms we just talked about, right? Lithium's going to give up its 1 electron, so we're going to have a lithium plus added to a fluorine minus, and that's what our compound is made out of. You can do that for magnesium as well. Magnesium has 2 Lewis dots. Chlorine has 7. So you can see that magnesium donates 1 to this chlorine, making it negative. But it has 1 left, right? So you need a second chlorine present in order to take on that second electron for magnesium. And now the compound comes out neutral, right? So we will do some practice with this. Okay, let's try these 3. So as you're looking at things to combine, you kind of have to think through processes we've already done. Step 1, you're going to have to think, what's the charge? Okay, so for example, rubidium is going to form a 1+ charge. Oxygen is going to form a 2- charge. Now, the second thing you need to know is how many of each do I need in order to be neutral? Okay, so a 1+ and a 2- are not going to add up to be neutral, right? So how many of each do we need? We need 2 rubidiums. So our answer is going to be Rb2. The number that we need gets turned into the subscript O. Ta-da! All right, you can do this for polyatomic ions as well. Now, if you write the polyatomic ion, it should already come with a charge. Oops, not 2+, 2-. So you don't have to think through the charge as long as you know the polyatomic ion. Another plug for learning your polyatomic ions. Magnesium, you still have to think through 2+. So now we think, if I have a 2+ and a 2-, how many of each do I need to get to a 0? I need 1. So I'm going to use 1 magnesium. You can either write that subscript or leave it off. And then you need SO4. Remember, SO4 is a bundle. Once you write the bundle down, you're not going to write the charge because the charge is neutralized by magnesium's charge. You can either choose to write that bundle in parentheses to help you remember, or you can drop the parentheses since the subscript is a 1. So in your textbook, you won't see it in parentheses, but if you want to write it in parentheses, that's okay too. All right, this is going to be the hardest one by far. Try this one. Let's think through the charge of each, a 2 plus and a 3 minus. Let's think of how many of each we need in order to add them up and come out to be neutral. You're going to need, our least common denominator is going to be a 6, right? So you need 3 magnesiums and 2 phosphoruses. So you're going to write it as magnesium, and we need 3 of them, phosphorus, and we need 2 of them. And that's your answer. One thing to be careful of this is make sure the subscripts represent the number of each atom or ion that is present, not the charge. Make sure the subscript represents the number of each atom or ion that is present, not the charge. We need 3 magnesiums, so our subscript for magnesium is going to be a 3, not a 2. The 2 is a charge, right? We drop the 2. Charges get dropped. Now it's a neutral compound. We're going to write the subscripts as the number of each we need. Okay, so you're going to practice this today, and then we're going to practice it tomorrow together. So let me know what questions you have right now. I'll see you in class.